Dear learners, welcome to the course Antennas and Microwave Engineering. In this video, I am going to explain antenna beamwidth. Antenna beamwidth is one of the important parameters to describe the performance of an antenna. Basically, antenna beamwidth is a measure of the directivity of the antenna. Antenna beamwidth is an angular width in degrees. Antenna beamwidth measured on a radiation pattern of an antenna. Let's start our discussion with the definition of antenna beamwidth. The beamwidth of a pattern is defined as the angular separation between two identical points on opposite sides of the pattern maximum. This is the general diagram of radiation pattern of an antenna. Radiation pattern consists of major lobe and minor lobes. Maximum radiation occurs in the direction. Generally, there are two types of beamwidth measured on major lobe: half-power beamwidth and Fresnel beamwidth. We are going to discuss one by one. Half-power beamwidth. Half-power beamwidth is an angular width in degrees measured on major lobe of its radiation pattern at half-power points, that is, half of its maximum value. At these half-power points, the field intensity equals to 1 by root 2 or 0.707 times of its maximum value. Half-power beamwidth is otherwise called as 3 dB beamwidth, since 3 dB down from maximum value. Directivity is inversely proportional to beamwidth. This is the antenna power pattern in polar coordinates. In order to find out half-power beamwidth, we are going to mark half-power points on major lobe. Here, P is the point at which maximum power is radiated. Here, P1 and P2 are marked as half-power points. What is meant by half-power points? Half-power points means half of its maximum value. Half-power points can be obtained by taking 3 dB down from the maximum value. Here, this point P indicates the maximum value. From the point P, half-power points are obtained by taking 3 dB down the maximum value. Here P is the maximum value, and from the point P, take the 3 dB line. These are the points on the major lobe, which is 3 dB down from the main maximum value. Once mark the points P1 and P2, we can draw the straight line from the major lobe. We can draw the straight line from the origin to the points. This is the origin. From the point origin to the point P, we draw a straight line. Okay. And this is the angular separation between the points P1 and P2. This is nothing but half-power beamwidth. So now we can understand the term half-power beamwidth. Half-power beamwidth is the angular width in degrees between the points on a major lobe of a radiation pattern where the radiated power decreases to half of its maximum value. It is also called as 3 dB beamwidth. From this figure, it is clear that the power is maximum at point P, but at points P1 and P2, the power is 3 dB down the maximum power. This is the antenna power rate pattern in rectangular coordinates and in logarithmic scale. So, as we discussed, this is the point P. It indicates the maximum radiated power at this point, and we mark the point P1 and P2 of the 3 dB down from the maximum value. We called the beamwidth. We measure the angular separation between the points P1 and P2. Next term is Fresnel beamwidth. The angular width between first nulls or first side lobes is known as beamwidth between first nulls, otherwise called as Fresnel beamwidth. It is denoted as FNBW or PWFN. After radiation, where the first null occurs, here it is, first null occurs. So we find the angular separation between these two first nulls is called as a first null beamwidth. It is the beamwidth that is minus 10 dB down from the pattern maxima. Approximately it is 10 dB down from the maximum value. Now I am going to explain the relation between directivity and beamwidth. Already I said directivity is inversely proportional to beamwidth. Okay. So now we are going to derive the relation between directivity and beamwidth. D is equal to 4 pi by omega A. Omega A is the beam area or beam solid angle. Beam area is nothing but the product of half-power beamwidth in horizontal plane and half-power beamwidth in vertical plane. That means half-power beamwidth in E plane and half-power beamwidth in H plane. It is represented as D is equal to theta E and theta H. It is the product of theta E and theta H, where theta E and theta are in radians. D is equal to 4 pi by theta E, theta H, if theta E and theta H are in radians. Suppose if theta E and theta H are in degrees, we can represent directivity D is equal to 41,253 divided by theta degree, 5 degree. Theta HP, 5 HP are nothing but half-power beamwidth in E plane and half-power beamwidth in H plane. So with the help of this relation 1 radian is equal to 57.3 degree, we can obtain D is equal to 41,253 divided by theta E, theta H in degrees. This is the relationship between directivity and beamwidth. There are three factors affecting antenna beamwidth. One is shape of the radiation pattern, another one is wavelength, the third one is dimension. Shape of the radiation pattern, for example, we consider this is the radiation pattern of one antenna. For example, we measure the angular width here. This is the angular width. And suppose if the radiation pattern is like this, the beamwidth increases. So therefore, the directivity of the antenna decreases. Directivity decreases. If beamwidth increases, directivity decreases. So from the shape of the radiation pattern, determines beamwidth. Beamwidth is nothing but angular space between the 2 points, and wavelength and dimensions. And application. What are the uses to measure antenna beamwidth? One is, whenever beamwidth is narrow, we have maximum direction. We can transmit a signal at a longer distance. So, beamwidth plays a vital role in direction finding application. Thank you.